Hello students, we are going to discuss about measurement of thermal conductivity. First instrument, gas analyzer. This figure shows that basic thermal conductivity gas analyzer circuit. It is a Wheatstone bridge formed with two sensing resistors acting as balanced leg of the bridge. One sensing resistor is surrounded by the sample gas to be analyzed, and another resistor is surrounded by the reference gas. Reference gas means that is oxygen. Both gases are maintained at the same condition. What are the conditions? Pressure and temperature. Both are same. Initially, the Wheatstone bridge is balanced by exposing both sample and reference resistor to same gas. The bridge is balanced by adjusting resistor capital Q, that is voltage outlet is equal to 0. In next step, the resistor are exposed to the gas sample and the reference gas sample. If the gas sample contains element having a different thermal conductivity than the reference gas sample, the Wheatstone bridge will be unbalanced. So, voltage out is given in terms of the thermal conductivity. Second method, FITCH method. This figure shows that FITCH method. This method developed by FITCH is used to measure the materials of low thermal conductivity by using a plane source of heat. This method consists of two components. One is heat source, another one heat receiver. Heat source is a vessel filled with a constant temperature liquid that functions as a sink. Heat receiver is a sink in the form of a copper plug, insulated all sides, but the one facing the vessel. Roles of the heat source and the heat receiver can be changed if the vessel is at temperature lower than that of the copper block. The specimen is interposed between the vessel and the open face of the plug. The sample is firstly in thermal equilibrium with the copper block. This is shown in figure. Refer this diagram. The vessel is brought into contact with the specimen under a temperature differential. Temperature history of the copper block and the temperature of the bottom of the vessel are measured by thermocouples. So it is assumed to have a uniform temperature distribution. Change of time and the temperature are measured. With the help of these parameters, determine the thermal conductivity of the specimen. This method is generally used for measuring the conductivity of food and especially small sized specimen. This method is not practical for use at a high temperature. In this method, either a line heat source or one or more heat sources are used. Next method, laser flash method. This figure shows that laser flash method. This is most commonly used method for determining the thermal properties of solid. The method can investigate two properties of glasses, metal and ceramic without significant limitation due to uncertainties of the achievable measurement. The property can be measured in a temperature range between -100 to 3000 degree Celsius. In this method, the thermal diffusivity, that is alpha, is determined given specific heat capacity and density of material. The thermal conductivity can be calculated by using thermal diffusivity, specific heat capacity and density under adiabatic condition. An instantaneous heat pulse is generated by the laser energy. Thermal diffusivity is calculated based on the thickness of the specimen and the time. Timing, that is the half of the time. This value represents the time required for the backside surface temperature to reach a value equal to half its maximum value. In this method, laser pulse is sent to the front side of the specimen and the temperature change on the backside is measured. Method is conducted through heating a specimen with a short laser pulse, that is width is very less on the front side of the specimen. Temperature increase at its near side is measured and determined. Advantages of this method. The laser flash method has the advantage of involving neither temperature nor heat flow measurement for the determination of a thermal property. The measurement of the thermal diffusivity, that is alpha, is calculated based on the relative temperature change as a function of time only. Main result of this fact is that even at a high temperature, the relative measurement uncertainties in the 3 to 5% range can be achieved. Thank you for your attention.